Understanding acceleration. We all have heard the word acceleration, and we have a vague idea that it has something to do with speeding up, or perhaps you've heard the word deceleration, which makes us think of slowing down. So we know that acceleration has something to do with these two things, speeding up and slowing down. In other words, changing our velocity. Changing velocity. In fact, a better way to think of acceleration is in terms of changing velocity. If something's changing in its velocity, then the acceleration that it has will equal the rate of change of its velocity. How quickly rate of change in velocity divided by or compared to the change in time. How quickly is the velocity changing? So this is the best way to think of it. Understanding acceleration. Understanding acceleration. Acceleration is a word we commonly hear in English. In your car, you step on the accelerator. And when you step on the accelerator with the gas pedal, what it does is it makes your car go faster. It changes the speed of your car. So we often think of speeding up as a kind of acceleration. And, of course, the opposite of that might be slowing down. Slowing down is a deceleration, but it technically means the same thing. In physics, we often just use the word acceleration to describe both of those things. So acceleration, then, has to do with speeding up or slowing down. But a better way of thinking of it is to define it like this. Acceleration is equal to the rate of change in velocity. Velocity tells us how quickly you're moving from place to place, and if you change that, if you change your velocity, then that would mean that you have to accelerate. And the rate of change implies that we want to know how much time is involved. How quickly are you changing your velocity? And so another way of writing that is this. Acceleration can be thought of as the change in velocity, whatever the change in your velocity might be, divided by or compared to the time involved in making that change. Now, we can write this English sentence or this English phrase with mathematics. We can say that acceleration equals the change in your velocity, change, delta v, divided by the change in time, delta t. And of course, what that means is that velocity equals the change in velocity, acceleration equals v2 take away v1. This expression means how much has your velocity changed, or what's the difference between your first velocity and your second velocity. And then the amount of time involved could be considered to be a t. You might think that we should write t2 minus t1 because of the delta sign. And technically you would be correct. But if we consider the fact that whenever you time something, you usually start your stopwatch at 0. So T1 is always going to end up being a 0 in most cases. And then we can just kind of simplify the bottom of this by thinking about T as representing the time involved. And so that's a bit of a simpler way of looking at the expression. Okay. If we draw ourselves a little graph right here, and we call this we'll just do a simple graph. We'll graph velocities and times, and let's plot a little thing. Let's say that something is starting off with this velocity, doesn't matter what it is, and it moves over here with this velocity. Then we can look at the change in time and the change in the velocity. Let me fix that line. I don't want to go quite so far down. Let's go to here. This represents, if you see there's velocity 1 and then velocity 2, this represents the change in velocity, or delta V. Right? I could call this V1, it's the starting velocity, and over here, whatever that number was could be V2. And so to get this number in red, delta V, that would be V2 take away V1. And if I look at the bottom, I can see that this line right here is equal to the time involved, because it's measuring along the t-axis. But if you recall from your math, this number over here, this red number, is also called the rise. And the green number is also called the run. And if we wanted to find the slope of that blue line, the slope would be rise over run. And that would end up being V2 take away V1, that was the rise in red, and the run is the time involved in green. And that's exactly what we have over here, which means that acceleration is equal to the slope of a line on a velocity time graph. Okay, I'll write that down for you. Acceleration is equal to the slope of a line on a velocity time graph. Velocity versus time graph. So that's another convenient way to think of. Anyway, now that we have an expression for how to calculate accelerations, let's look at one more thing. Let's look at what happens when you start thinking about positive and negative accelerations. Up until now, we've talked about displacements and velocities, and we know that positives and negatives can actually indicate direction. So we can use these to indicate direction. But acceleration is a little bit odd, because you could also use positives and negatives to distinguish between speeding up and slowing down. And so we get a little bit of confusion as to what a negative might mean. I'll give you an example. If I were simply to write an acceleration of -6 meters per second squared, which incidentally means 6 meters per second faster every second. Does this negative sign mean that I'm going left and faster? Or does this negative sign mean that I'm going right, but I'm slowing down? How can we tell the difference? And that's what we have to kind of think about when we do accelerations. And so, what I want to do is draw a little chart for you. And on the little chart, you'll have 4 things. we're going to put speeding up on this part, and we'll put slowing down on this side. And then over here we'll make two more on the side. Here we'll put going to the right, and here we'll put going to the left. Now, usually we consider going to the right to be positive, and we consider going to the left to be negative. We also consider slowing down to be negative. Well, let me use a different color for that one. Maybe that will be a better idea. Let's use green. Negative for slowing down, positive for speeding up. Let's see what happens if we use the chart to combine them. In the first square, we would have a positive because of the moving right, and a positive because of the speeding up. And so that means, if you think about when you multiply positive times a positive, that's positive. If we look at the next chart, we would have a positive because we're moving to the right, but we would have a negative because of the slowing down. So that means that you would end up with a negative acceleration. On the next chart, or next level, we have a negative for moving left, but we have speeding up, which is plus. So that equals negative. And then in the last box, we have a negative for left, and we have a negative for slowing down, wrong color, let's fix that, a negative for slowing down, and we get two negatives. When you multiply, make a positive. So from this little chart, we can see two important things. In terms of the sign, the plus or the minus, speeding up to the right is a positive acceleration, and that is exactly the same as slowing down to the left. Mathematically, it's exactly the same. And we then see that slowing down to the right, see, those are both positive accelerations. Slowing down right towards the right-hand side is exactly the same as speeding up to the left, because those both give us negatives. Well, how can this be? How can we have the same idea? Here's what I want you to think about. Imagine if you were running. Here you are, and here you are running very quickly, and you are running in this direction with a little arrow here across the board. If you were running very fast, then imagine someone had tied a little rope around your waist and was pulling backwards against you. So this is kind of like the acceleration. I want you to envision the acceleration like a string pulling back. We'll learn later that accelerations are caused by forces, and so it's okay to think of them as little pulls or pushes. If the string was pulling on you and you were moving very fast, well, what would happen is you would be slowing down because that string was pulling you back. So then you'd be slowing down, slower by the time you got to here, slower. Eventually, you would get to a point where you were going so slow that you stopped. But that would not be the end, because if I kept pulling in the same direction with that string, you would spin around and I would actually start dragging you backwards. And if I pulled and pulled and pulled, you would be going backwards, and you'd be going faster and faster and faster. Faster and faster as I pulled you back. And I never once changed the direction of my pull, my acceleration. this is an acceleration in a negative direction, isn't it? It's a negative to the left. But look what it can do. If you are moving right, it can pull on you and cause you to slow down until you stop. But it can also make you go faster to the left. So a negative acceleration can do both of those things. It can slow you down to the right, or it can speed you up to the left. Slow you down to the right, speed you up to the left. Negative acceleration. And of course, if we envision pulling the string the other way, I think you can pretty much guess how that would look. If you were going to start over here, and you were going to run this way, and you're going to run across like this. Eventually, well, let's put our little string here, and let's pull back this way. We'll pull to the right. If you were moving very fast, and then the string began to pull, you would move slower as you moved across, and slower until finally you stopped because of that string that's pulling you this way. But that would not be the end of the story, because after you stop, if you kept on pulling with this string, then you would end up being pulled backwards faster and faster and faster. And so you'd be stopped, but then as you got pulled backwards, you would start going faster and faster. So what's happening is, with this acceleration pulling to the right in a positive direction. Okay? Now accelerations don't technically pull. It's forces that pull, but forces cause acceleration. So you can think of the acceleration like a little string dragging you in that direction. If you are moving in the negative direction, then you will be slowing down to the left. And then after that, you will begin to speed up to the right. Slowing down to the left, speeding up to the right equals positive acceleration. So that's another way of thinking about it. Another little trick you can use to help you when you're trying to look at problems is to look at your velocity. If your velocity, right, if we look at our picture right here, if our velocity is to the left, see this guy going left here, then our acceleration is to the right. So if velocity is a different sign, or is opposite, it's different from the acceleration, guess what that means? It means you would be slowing down. And if your velocity is the same sign as your acceleration, same as acceleration, then that would indicate that you were speeding up. So, one more little summary then. If you have negative velocity and you have positive acceleration, they are not the same, which means you're slowing down. And you can tell the direction by looking at the sign in front of the velocity. Slowing down, and this is the sign you would look at to determine which way you were going, right? You'd be slowing down left. If you had a negative velocity and a negative acceleration, those are the same, so that would mean speeding up left. And again, what tells me it's left is the sign on the velocity, not the sign on the acceleration. If you have a positive velocity and a negative acceleration, you would be slowing down because the two signs are opposite, but this velocity sign tells me that you would be moving to the right, slowing down to the right. And the last one is positive velocity, positive acceleration. They are the same. That means speeding up. And if you look at the sign on the velocity, it means to the right. So there's another way of keeping it all straight in your head. And that's the story of acceleration.